logarithms.
Mhm.
So the natural log of 5 to the t, actually, I guess let me start. It's 5 to the t equals 8. You take the natural log of both sides. When the natural logarithm is applied, you can put
T
the
goes
t
in
out
front.
in front. So t natural log of 5 equals natural log of 8.
And you just divide.
Yeah. And it's just around your answer to 3 decimal places. Yeah, so
Get my calculator out so I can follow along. All right.
let me grab my calculator also, just in case we need to compare answers here. Log of 8 over log of 5. I get 1.292.
LMAO divided by natural log of 5. Yeah, I get 1.29.
Perfect. 3 decimal
Yeah.
places.
So 1.292. So that doesn't need to change. Correct. Sharing again real quick.
Okay.
All right.
Okay, yeah. Same style of question here. Let me snip it in. All right, so I'm going to share my screen here. And again, you're solving for t using natural logarithms. So to do this, you have to make an additional step here. You have to first divide by 10. Okay, because you want to isolate the exponential thing. So it's 9 equals 1.5 to the power of t. And then you take the natural log of both sides. And then that t comes out in front. So you have t natural log of 1.5, natural log of 9.
So
And
now you get your ln 9 divided by
exactly.
okay.
So again,
I
you go
like
to your,
these types of questions because I can actually like keep on repeating it until I get it. So I
yeah,
get 5.419 and it doesn't need to change.
yep, that looks good to me.
9, correct. So I'm gonna share again. All right. So this looks like this T just come out to the front and then, or do I divide by 2 first?
You divide by 2 first.
Okay, so 3/2 equals e to the t, so then
So this time,
t natural log of e. Okay, so ln 3/2 basically.
yeah, it undoes the e on the right hand side.
Ln 3/2, and I get 0.4005.
Yes,
Let's see if that's correct. All right, that one was pretty easy.
good.
All right.
So this is very similar. I could probably talk you through it.
Mhm.
I'm working these out also on my side in case you want to look at the notes later. But first thing here is you're going to divide both sides by 10. I'm sorry, by 50.
Oh, the 50. Oh, okay. So 1/5 on the left side, and they get e to the negative 0.04 t power.
Exactly. So you use ln again, and on the right you get 0.04 t. So you negative 0.04 t. So you end up dividing both sides by negative 0.04.
Oh, okay. So say natural log of 1/5 is that negative, yeah, and negative 1.6, and then divide by that negative 0.04 basically, right? I get
Yeah,
40.236.
6. Perfect. That's what I get also.
40.236. Submitted, correct. It's at least something different. Or maybe not.
Not really. You're doing the same thing as the last problem. This time you're going to move the
20
20 to
divided
the
by
other.
3.
Yep.
All right, so 6.6. And 20 divided by 3, then
Take the natural log of both sides. Yeah,
that's log of both sides. So ln of 20 over 3 basically.
that's right. And I get 1.897.
I get that too. 1.897. submitted. All right. All right, P equals 7 times 2.2 in the form. Oh, I'm not sure how to do this.
Yeah, let me share my screen here. This one requires a little bit more explanation than the last one. It's not that bad though. It really won't take very long to explain. It was kind of a useful thing to do a million years ago before calculators were more common, but what they want you to do here is these two forms here, maybe actually let me just parse them a little bit more. So 7, 2.2 to the T, P0, E to the K to the T. Okay, so I made a small rewrite, but this part, I'll do it in red here if I can get to it. This part in red, we're going to set equal to each other. So you're going to literally set 2.2 equal to E to the K. How do you solve for K? How do you undo E? ln.
Oh,
right?
yeah, ln. Yeah.
So you take the natural log of both sides equals natural log of E to the K. It becomes just K. So this right here is your K value. So that's not the final answer, but we need to get
That's
that
part
number.
of it.
Yeah. So let me get that number for you. What does it say here? 4 decimal places. 0.78.
Okay. 7885.
5. Yeah. So now what do they want? They want P. So they want this equation. So 7 7e to the 0.7885 t.
Is that it?
That's it.
Oh, I thought that we were about to like start, I don't know, putting something else in there. No, I was just waiting for the but and start doing more. Let's see. So E to the 0. Should I do like a parentheses and put 0.7785?
You can. I noticed last time we did this, it took them away sometimes. So
yeah, it's a little bizarre. So make sure that I put that in correctly and submit it. And that is correct. All right. Sharing for the last problem for this set.
all right. Yeah. So I'll snip this in. It likely just looks more complicated than it actually is. But,
That's what I'm thinking too.
But I will be happy to help as usual. Let me share my screen. There we go. Oops, didn't share yet. And I'm going to do this in red just because it's the black backdrop there. Okay, so it says the concentration decays exponentially at a continuous rate of 2.54. So like it's that PERT, PE to the RT. And we'll just assume that P is 100. If they don't give you P, 100 is reasonable because that means 100% is there at the beginning. And because it decays, that means that the R or the K is negative.
Oh, all right.
So E to the minus 0.0254 T. Okay, so this is our formula. This is not the answer to this first question, but that's the formula. Now we can answer this question. It wants to know when it's half. So half means that 50 equals 100 E to the minus 0.0254 T. And you're solving for T.
Do you what do you do here? Do you take
You divide both sides by 100.
Oh yeah, the first step. I always forget that. So you have half.
So you have half equals E to the minus 0.0254 T. And then you take the natural log of both sides.
Oh, all right. So then you're left with 11. Let me pull up the number 1/2. I get negative 0.6931
Sure,
5.
but we're not done yet. We gotta undo this
Yeah,
on
for
the
undoing
right.
it,
So
for dividing it by it.
yep. And then that's the number they want there. And that's the one where they say round to the nearest integer.
254. Okay. I get 27.28, 27.2893.
It says nearest integer, so just 27.
Oh, all right. So just say that. All right.
Okay, at what distance from the road is the concentration of NO2 70% of what it is on the road?
Did you just replace that?
Well, instead of 50, I think it wants for 70. Just double
Yeah.
checking here. So instead of 1/2, it becomes 7/10.
Mhm. So I'll put ln 7 divided by 10 and then divided by that parentheses negative 0.0254 and I get 14. And that's done for that. I'll share my screen for the last homework thing. Is right about here. Come on, man, work me here. Here we go.
Did that work?
Yeah, I already got
Okay,
it. I'm just
great.
pulling up another homework real quick.
Sounds good.
Try to blast through it really quickly. Since we blasted through that last one really
Yeah.
quickly too. All right, sharing screen right about now.
Okay, yeah. Find the derivative of this. So let me just snip this into my screen. Some of this is review, some of this is new
Really
stuff.
new.
Yeah, so let me share my screen and we can talk about that. Okay, so the one that is familiar is this 4x squared. The derivative of 4x squared. We were doing that last week or last time. Remember the power rule? You bring that 2 down, you multiply it, and then you subtract 1 from the exponent. Do you remember that?
Yes.
Okay, so that's what we're using here. We're using the power rule, and you want to get so comfortable with the power rule that you actually just tell me, oh, it's 8x, Matthew. You don't want to do all this each time. Like maybe mentally you want to say, oh yeah, it's 2 times 4, and I subtract 1, but you just want to write that.
So that next one is let's see. So is it just x times 7, or do you not do the power roll for the 70x?
So this one is different. So if y equals e to the x, y prime equals e to the x. So this is the only function whose derivative is itself. And then the constant just comes with it.
That's interesting. 7e to the x.
Yeah, and this is critical. Like these are one of those things. Like this is the part of the course where you're trying to really get these derivative rules down, because you're gonna reuse them over and over again.
Sharing screen.
Yeah, so this one, like the first one, you know how to do. You know how to find the derivative of x cubed, but the other one you do not know the rule for yet.
Is x cubed just 3x basically, or what do you do?
You subtract 1 from the exponent.
Oh, that's it. Oh,
Yeah, so it's 3x squared, right? Because it's you bring the 3 down.
Oh yeah.
3x squared, because you subtract 1. Now, when your y is equal to a to the x, okay, which is what you have here, your derivative is itself times the natural log of a.
All right. So this is 3 to the x times log 3.
Natural log of 3, yeah.
And do I put that down, or do I have to expand on it?
What do you mean? This is.
Oh, that's the full answer. Okay.
Yeah.
I'm just making sure that it wasn't like anything like more to it.
Yeah. It's and again, this is another one to remember. So there's now 3 derivative rules to remember that you before only had 2 or 1 maybe.
That's correct. There we go.
All right, I'll snip this. That first one, 4 to the x, I mean, that's very much like the last one we just did.
Is that okay? So the last one we had, what was it again? It was 3 to the x, natural log of 3. So is this the same thing for
It's exactly the
to
same
the
thing.
x, natural log of 4? Okay.
Yes.
So I'll write that down because I already know that. So 4 to the x. And it's just multiplied, right? Just yeah.
Yes.
Just
Yeah, it's a dot multiply. So this 10 over x cubed, you want to do a rewrite. You want to write it as 10x to the minus 3 power as the original. This is not the derivative. This is the original. So the derivative is you take this minus 3 and you multiply it by the 10. So you get minus 30x, and then you subtract 1 from this. So it's minus 4.
oh, okay.
10 times minus 3x to the minus 3 minus 1 power.
Yeah, I need to keep on getting more comfortable with that power rule.
Yes.
Minus.
This whole course is about taking derivatives. Like don't let you be misled. Like you're gonna have to take derivatives. You're gonna have to get really fast at it. That's the key to being successful in this course.
All right, that's correct. And I'm sharing my screen.
Okay. All right, let me grab a snip of this. Okay, the amount of coffee in the body is described by this function here. They want you to first find the derivative. Okay, so the derivative of this right here. Okay.
Okay.
So the 90 just comes along because it's a constant. It just comes along. The derivative of E is itself. Okay, but there's one more little thing here. You have to take the derivative of the inside function, which is what's called the chain rule. I don't know if you've covered that in class. It doesn't seem like it, but I'm not sure. So the derivative of 0.17t is negative 0.17t is just the negative 0.17. So you have to take the derivative of the inside function. So it's kind of like this, Jack. If I tell you that y equals e to the u, y prime is e to the u times u prime. Whatever the derivative of this thing up here is, I have to put out in front.
Oh, all right. So it's times
Negative 0.17.
Okay.
Now you do have to, it looks like in this class, you got to multiply these for this assignment here. So it ends up simplifying to negative 15.3 e to the minus 0.17 t.
Yeah, 15. So e to the minus
And then what?
t.
What?
All right.
Okay, now the next part, it says find f of 2. F of 2 is referring to the original function. So that's 90e to the minus 0.17 times 2. And we need to round it to 2 decimal places. So that I get 64.06. Now your units are the whatever the units of A are. Looks like it's going to be milligrams for that one. It's a 6. The derivative, we're going to use the derivative function, that minus 15.3 e to the minus 0.17 times 2. And I get negative 10.89. Now the derivative is always a rate. So it's gonna be milligrams per. Do you see that there's hours?
Yeah, milligrams per hour.
Exactly.
All right. And that is correct. Just shared my screen for the next one.
All right. Population of Hungary. Okay. I'm just gonna grab all this and share my screen. All right, share screen. Yes, yes. Okay, what does the model predict for the population of Hungary in July 2020? So they're saying that t equals 0 is for 2014. So 2020 is t equals 6. And this is the population function up here at the top. So the population is 9.919.998 to the power of 6. And then whatever that is, we're gonna round it to 2 decimal places for this answer here.
So I'll do along with you that 9.19 times 0.998 and then to the power of 6. I get 9.800565555.
Just 2 decimal places.
All right.
Okay, now it says how fast in people per year. When it says how fast or how slow, that's the derivative. You have to train yourself to do that.
Okay.
So you have to get the derivative of this function up here. Now this one is an a to the t power. So your derivative, your p prime is 9.919. It's that original exponential times the natural log of the base, 0.998.
Okay. I'll pull that up. So then I take that number that we got and multiply it by all that.
So
I get negative. Do you get a negative?
it's going to be negative this time because that log of 0.998 is less than 0. And if you recall, the growth actually changes on that. So I get now, see how this is people per year?
Yeah.
So the original one was in millions.
And this
So
is
we
just
need-
a single person per year. So do we multiply this by a number?
We have to multiply by 10 to the 6th or 1 million.
Times 1 million. Okay, so 1, 2.
So I get 19,621.
620.8. I guess I did that wrong. What does it say? Give you around. I get negative 19,620.
Right.
0.8.
But because it's already decreasing, you don't have to include the negative.
Oh, that's fine.
Although we saw one the other day that seemed to violate that where you had to put the negative in, but hopefully this one's been coded a little better.
Yeah, it did what it was supposed to this time. All right, just shared my screen.
Okay. Yeah, sounds good here. Just snip this in. All right, share screen. Yes. Okay, the temperature, they give you a, oops, what's going on here? The temperature of this thing is given by this function here, this h equals 40 plus 30 e to the minus 2t. And they want the rate. Rate means derivative. The rate is the derivative. The derivative of a constant is always 0. So this 40 is 0. The derivative of the 40 is 0. Now you don't write 0, but you should know that. The derivative of this e, okay, remember I mentioned this earlier. When you have e to the u, the derivative is e to the u times u prime. So the derivative of this 30e to the minus 2t is itself, but then you have to multiply by the derivative of the inside function. The derivative of minus 2t is minus 2. So if you did want to simplify, it's minus 60e to the minus 2t.
Oh, okay.
And this is a chain rule thing. I mean, I don't think you covered that yet based on what I'm seeing, but you will cover it shortly, like maybe your next class.
Mhm.
So it'll make more sense. Okay, what is the sign of the derivative? So do you see how this negative 60 is out in front?
Yeah.
The sign of this is always negative because the derivative is always negative, because this e part is always positive, but this part out in front is always negative. So a negative times a positive is always
Negative.
negative. Okay, so the next question is asking you for when for t greater than or equal to 0 is the magnitude of dh dt largest. They're basically asking you to look at this graph and figure out, well, when is it the biggest number? It's kind of an advanced question here. The answer is 0, although I don't know how to really justify it without showing you more calculus than you already know. But if you think, okay, well, t is 0, this becomes negative 60e to the minus 2 times 0, which is negative 60. But since they want the magnitude, that means the absolute value, which is 60. Now, if you put in any other number, like let's say you put in t equals 1,000.
Yeah.
It's negative 60e to the minus 2 times 1,000. This becomes negative 60 over e to the 2,000. And even doing magnitude, you're doing negative 60 or 60 over, like e to the 2,000 is a huge number. This is basically 0. This goes to 0. So the graph of this thing, the magnitude of the graph of this thing, it starts at 60 and it goes to 0 like that.
I see what you mean.
But I mean, if you understood like 50% of that, you're doing great. You're not going to get them on the test. You're going to be asked to do derivatives over and over again in this class.
And I'll practice derivatives.
All right. Wow. They really want you to do a lot of this. Okay.
Yeah, it's annoying.
Yeah, it's just the real practice you need right now is taking derivatives, not on these application problems quite yet. You just want to know how to take a derivative over and over and over again. All right, so let me share my screen here and we'll so they give you an equation and they want you to evaluate the equation at 0. So that's this notation right here. That's the original function. That's 480 1.1 to the power of 0, and that equals 480. Now let's go ahead and do 22 next, because that's the original function. That's 480 1.1 to the power of 22. And this time it wants you to round to the nearest integer. So that should be fairly straightforward to figure out.
All right.
480 times 1.1 to the power of 22. And so that is 3907. Excuse me. So we can actually go down here and answer some of these questions. We're going to come back and do the derivative. In 2000, the solar production was 480.
All right.
Okay. In 2022, solar production will be 3907.
All right.
Now we're going to go find the derivative. So we're finding the derivative of this function right up here. The derivative of this f prime of t is 480 1.1 t. Now, because it's a base of 1.1 or base of anything, you have to multiply by the natural log of the base. Does that make sense? That's that a. This is the d dx of a to the x. It's always a to the x natural log of a.
Oh, all right.
It's that one right there. Oops, sorry about that. So now to do f prime of 0, it's 480 1.1 to the power of 0 natural log of 1.1, which we'll get a number for.
So that 1.1 to the 0 is just 1, right?
0. Yeah, 1.1 to 0 is 1.
Okay.
But that's times 480.
Which is just 480. So 480 natural log of 1.1. And I get 45.75.
Yep. So it's round to the nearest integer.
So it's 46 basically.
Yep. And then the next one is f prime at 22. And it's the same formula. You're just using 22 instead of 0 for your
Mhm.
value of t.
So I'll do the 1.1 parentheses 22. You get that. You multiply by 480. And then you multiply this big number times natural log of 1.1, right?
Yes.
All right. I end up getting 372.
Perfect. Okay. All right. So now we can go down to fill in the other blanks. It says in the year 2000, solar power produced was 480, and it was increasing at, that's derivative, 46 megawatts per hour. And then obviously the other value goes here. You are going to be expected to write a sentence like this, the dreaded interpret question on an exam.
Hmm.
If it's not multiple choice, or if it's multiple choice, they'll give you a couple and you got to choose. But almost always you have to write a interpret thing.
All right. Sounds about right.
Okay, yeah, let me snip this. So it looks like we're moving to kind of it's related, but it's kind of going back down to an easier kind of question here. So let's do this. All right, let me share my screen. So the rules, they just want the derivative of this thing. And again, the derivative of a constant is always 0. So the derivative is this 3 is 0. The derivative of the natural log of x is 1 over x. So the derivative of this natural log of p is 1 over p. Because this subtraction sign is out in front, it also goes with it. It's negative.
Oh,
So this is another, another derivative rule to learn, to remember here. I'll try and write them out as we go so that you can see which ones we're using.
and here are the last two.
All right. All right, let me share my screen. Okay, so this one, if you're seeing my screen, it says R of Q equals 4 natural log of Q. Whenever you have a constant, the constant just comes with it when you're taking the derivative, especially when it's multiplying. The derivative of natural log of Q, though, d dx of natural log of x is always 1 over x. So the derivative of natural log of Q is 1 over x. So the simplification here is 4 over, it's not x though, it's Q, because that's the variable in this particular problem.
Oh, okay. The last one.
Okay, this is a good question. It's got elements of what you did in your last, or the lesson before the last one. So let me share my screen here. So what I mean by that is, let me just make it a little larger, is you're doing both a power rule. This is a power rule question because it's a variable to an exponent. So the derivative is you bring the 9 down, Q, and then you subtract 1 from the exponent, so it's to the power of 8.
All right.
Minus, okay, the 7 just comes with it, and the natural log of Q, the derivative of that is 1 over Q. And that's the one you got to remember. It's weird, it's awkward, like what do you mean? But that's just the way it is. So this is 9Q to the power of 8 minus 7 over Q.
All right. And that's everything I wanted to do today. Thank you so much for your time.
You're welcome. Thanks, Jack. Have a great night. Bye now.
You too. Bye-bye.